Good morning, everyone. The topic I'd like to talk today is fracture analysis of stiffened laminate composite plates. My name is Chyanbin from National Cheng Kung University. Actually, this work was done by my PhD students, Mr. Xu, when he stayed in the Technical University of Darmstadt, work with Professor Mittelstedt. For the laminate plates, due to the anisotropy of each layer and the possible non-symmetric stacking of the lamina, usually the bending extensional coupling cannot be avoided. And if you think the plate is a thick plate, the transverse shear deformation cannot be ignored. And if you consider further about the stiffened plates, the plates attached with a single or multiple cylinder beams. So generally the structural rigidity and stability and load carrying capacity can be enhanced. So due to the complexity raised by the lamination, the bending extensional coupling will occur, and due to the thick plates, the transverse shear deformation cannot be avoided. And due to the stiffener, the beam plate interaction, the mixed mode fracture, such as the opening, shearing, bending, twisting modes, usually cannot be avoided. So the problem becomes very complicated. So usually, this kind of fracture analysis will be done by using the finite element methods. I think most of you will be very familiar with the finite element methods, but all of you should know that you need to have a very, very fine mesh near the crack tip. So sometimes we like to have a new method. So when we consider about the new method, we consider about the boundary element method. But we all believe that this stiffened plate is not so unusual. It's very usual. Should have somebody already done this. But when we search about the literature, no one did this. So we try to do this. And the benefit of this boundary element, it can reduce the problem dimension by 1. But for the boundary element, the key point is the fundamental solution. Usually, people use the conventional boundary element, use the conventional fundamental solution. For that kind of boundary element, the mesh are required along all the boundaries, including the crack surface. So you still need a very fine mesh near the crack. But if you have a spatial fundamental solution for the crack, then no mesh are required along the crack surface. So this will increase the accuracy and efficiency. So this is what we like to do. Okay, so in this study, we try to develop a boundary element for stiffened laminate composite plates. So for the boundary elements, you can think about the thick or thin laminate plate with a conventional fundamental solution. That one, you still need the mesh along the crack tip. But for the thin plate, you can consider about the spatial fundamental solution for the crack. And because we consider about the stiffened plate, so we need also consider about the beam with a conventional fundamental solution. So in this study, when we consider the stiffened plate, 2 different approaches are considered. One is a thick plate with conventional fundamental solution and thick beam with a conventional fundamental solution. The other is a thin with a spatial fundamental solution of the crack. Okay, for the laminate composite plates, you can consider the symmetric or unsymmetric laminates, and you can consider thin or thick laminate plates, and using based on different theory. The thin plate based upon the classical lamination theory, the thick plate based upon the first order shear deformation theory. For the thin laminate composite plate, we consider the 4 degrees of freedom per boundary node and 1 degree of freedom per corner. For the 4 degree of freedom, we consider 2 in-plane displacement interactions and 1 diffraction effective transverse shear force and 1 slope and bending moment along the plate boundary. And for the corner, we need to consider the corner force. And for the thick laminate plate, we consider 5 degree of freedom. It's much more simple than 4. Okay. And we already mentioned that for the thin plate, we have 4 degree of freedom per boundary node and 1 per corner. And we may consider 2 different kinds of the fundamental solution, one for the spatial purpose of the crack problem. For the thick plate, we have 5 degree of freedom per boundary node, but we don't need to consider about the corner. And for the fundamental solution, we are very sorry we do not have the spatial solution for the crack. So for this case, because this is very difficult to obtain this solution, so here now still not available. If you are interested in this, you may try. Okay. And for the beam, we also consider symmetrical or non-symmetrical, and we consider thick laminate, but this can be applied to the thin laminate plate, thin laminate beam. So the thick one based upon the Timosenko beam theory, the thin one based upon the Euler beam theory, but the thick one can be reduced to the thin one, so no problem. And the degree of freedom is 3 degree of freedom per boundary node. And the boundary fundamental solution is for the general purpose because we didn't consider the crack inside the stiffened, okay? And the main topic for us is a stiffened laminate composite plate. So we need to account for the perfect bonding condition. And so we established the displacement continuity and interaction load equivalent at their interface. This is required for their perfect bonding. Another thing we need to consider is the domain integral. Usually for the boundary integral, we only consider the boundary integral, but because the interaction between the beam and plate, so this cannot be avoided. So the domain integral, we need to consider they are related to the unknown interaction load. So we need to discretize each stiffener into a series of cells and using the quadratic interpolation. And by collecting the individual boundary integral equation for the plate and stiffener and employing the continuity and equivalent equation at the interface, we can construct entire system of linear equation to solve the stiffened plate problem. And if we got the nodal value of the displacement and traction on the boundary of the plate and at the end of the stiffeners, and as well as the interacted loading conditions, so the solution can be solved. And the complete solution for the crack plate can be calculated by using the nodal value. So this is the basic equation for the laminate composite plates. We consider the displacement field like this, and U0, V0, W0 denotes the displacement in the XYZ direction of the mid-plane. And Z here, you can see, means that the thickness distribution is a linear distribution for the displacement. And the beta X, beta Y here denotes the slope in the X and Y directions. And they are related to the transverse shear strain. So we consider the transverse shear strain for the thick plate. The kinematic equation will concern about the in-plane strain, curvature, and transverse shear strain. We say that the bending and stretching are coupled each other. And consecutive law is the usual law for the laminate composite plate, and equivalent equation are for the equivalent between the in-plane force, bending, twisting, and transverse shear force. And this is a boundary integral equation. From the index, you can see that for thin plate, the index is only 1, 2, 3, 4. That's we say that per node, only 4 degree of freedom. But here you have the extra term to consider about the corner force. And so you can see this boundary integral equation is much more complicated than the thick plate. For the thick plate, the boundary integral equation have exactly the same mathematical form as a two-dimensional analysis or three-dimensional analysis. So if we can develop the boundary element based upon the thick plate, it will be simpler than the thin plate. It will be simpler than the thin plate. Even their degree of freedom is higher than the thin plate, but it will be simple. But the difficulty one is to get the fundamental solution for the thick plate is much more difficult than the thin plate. So currently, we have the solution for the crack problem for thin plate, but for the thick plate, we still cannot get the solution. So this is a metric form for the boundary integral of the thick plate, and this is a degree of freedom for each node we show here. And this is a fundamental solution. We say that for the thick plate, we have the fundamental solution for the general purpose, but we still do not have the solution for the crack problem. And this is a fundamental solution for the crack problem, but this is for the thin plate, only for the thin plate. And we got this solution by using the complex variable method. But for the thick plate, it's still very difficult for us to develop the similar complex variable method to get this solution. So this is one we try to solve this problem. And this is for the bin, because we consider about the stiffened problem. And for the bin, you can see the fundamental solution is much more simple. And R here means the distance between the source point and field point. And we say that we consider about the stiffened plate. So we need to consider about the continuity condition. To assume the perfect bonding between the plate and stiffener, the continuity condition for the actual displacement by this equation, and consider about the rotation by this equation, and consider about the continuity of deflection is here. And we also need to consider about the equivalent of the interaction load, and they can be expressed by three equations in three different directions. One is in the actual direction, and the other is in the transverse direction. And this is for the bending moment. So this is the system equation for the stiffened plate. Very complicated insight, so I did not show the details of this matrix. And our target is a fractal analysis. So based upon the definition of the stress intense factor, they consider about the opening, searing, bending, and twisting mode, because we consider about the mixed modes fracture problem. So this is their definition. And this is the in-plane force. This is a bending moment. This is a twisting moment. This is the bending moment. R here is the distance ahead of the crack tip. This is their definition. But according to this definition, you need to have the data near the crack tip. But we say that if we use the spatial fundamental solution, we do not need to have the fine mesh near the crack tip. Even the entire plate inside, no mesh. So if only have this definition, there is no use for our, no spatial use for our developed boundary elements. So we need have a formula to calculate the stress intense factor through the nodal displacement and nodal traction on the boundary. This is quite important, because if you have the solution only on the boundary, and through this data, you can calculate the stress intense factor directly, then we don't need to have any mesh. This is the problem of the finite element. So we have this formula. And we derived this formula 4 years ago. And now it's very useful for us to do this work. This is a numerical example, and we did recently. And this is my conclusion. We say that our solution is really very agree with the final element solution generated by the software answers. And unlike the conventional final elements, requiring very complicated area meshes, only line meshes are involved in our boundary elements. And in view of the efficiency and accuracy, we say that our work is success. Thank you very much.
Thank you.